gives me a great pride to welcome Kent Berridge to give a talk today. Kent comes to us from University of Michigan, where he started working there in the mid-'80s and has, sort of steadily and quickly rise the ranks to become the James Olds Collegiate Professor of Psychology and Neuroscience. Before that, he was at Dalhousie, where he did a postdoc for 2 years, and got his PhD and his master's degree at University of Pennsylvania, and his bachelor's with honors at UC Davis. He's got several visiting appointments over the years, for example, at the University College of London, among others, and he's won some really prestigious awards along the way, including being named a AAAS Fellow, an APA Master Lecturer, Guggenheim Fellow, an APA Fellow in 2 divisions, an APS Fellow. Started off early on earning the Distinguished Scientific Early Career Award from the APA, and most recently he should be congratulated on receiving the Distinguished Scientific Contributions Award by the APA this year. Kent's work, I should also mention, I didn't want to bother counting all the publications he's had. He's extremely prolific. So instead I counted the pages. He's got about 10 pages of small font citations on his CV. Depending on whether you use Google or ISI, he's got somewhere between 20,000 to 35,000 citations and indices of really high numbers, 67 or 80, depending on how you count. I always like the Google numbers because they just make you feel better, but also I think they capture more and they're probably more realistic. Needless to say, he's an extremely accomplished person in his field and a true leader. His work sort of started early on asking questions about learn, taste, aversion, and palatability, doing some more physiological kinds of things focused on salt depletion, insulin secretion, glucose consumption, these sorts of things. But his sort of interest in liking sort of came relatively early on. One of his earlier papers titled "Rats Learn to Like the Taste of Morphine" kind of indicates that he was already thinking about not just how mechanisms of hunger, but how they relate to reward and things like liking and wanting, which is sort of one of the things that he's really very well known for. So his career has sort of taken him through asking questions about food reward and the brain substrates that underlie that. But he's also become interested in things like unconscious emotions and how that relates to liking. And so there's actually a lot of sort of similarities and common themes between all of these things that he's really developed over the years. As I said, the liking and the distinguishing between the liking, the wanting, and the learning is something that, well, not necessarily in the title of this talk, but I'm confident we'll hear about, which has really sort of been a centerpiece of a lot of the work that he's done, and developed that into understanding things like pleasure. He's got 2 of his more recent papers that I just love the titles on that kind of captivate things, are Pleasure Systems in the Brain, and then a commentary that he wrote on another paper called The Hunger Games, which is a fun one. The work that he's done has spoken to me most in that I'm really interested in understanding decisions on mating and when to mate and when not to mate. And some of the work, and we talked about this briefly earlier, that he's done really sort of speaks to me at a different level. It's not hunger, but sort of the liking and the wanting, the same neural mechanisms that appear to be regulating liking and wanting seem to be regulating decisions to mate, and maybe wanting to mate versus not wanting to mate. And so I've really sort of found his work to be really interesting and really broadly applicable. But of course, his work in understanding the mechanisms of this and how it relates to drug addiction has been really a top thing. So I don't want to take too much more time. Rather than me telling you what he's doing, we'll let Kent have the honors. He's going to talk to us today about delight, desire, and dread, generators in the brain. Please help me welcome Kent Berridge.
Thank you, Alex. That was a very generous introduction, much kinder than I deserve. And I'm certainly delighted to be here for the centennial celebration of Sigmund Freud's birthday. I hope you do this every 100 years. And it's been a pleasure these past couple of days meeting people, talking with people, and hearing about some of the really exciting work that's going on here at Cornell. It's a great department. It has been ever since Titchener, but many, many great accomplishments along the way. So I will talk about liking, wanting, and learning today, and some issues that I hope will be of interest on reward. There's really several points that I'd kind of like to talk about today that I hope will be of interest. First is that wanting can detach from liking and even sometimes from learning. Sort of one thing that's popped out over the last couple of decades is that a lot of the brain can generate wanting. A lot of the limbic system can generate intense, powerful wants of various kinds. So we'll talk about that. And the individuals differ in their susceptibility in ways that that feed into addictions. Another point for today is that liking for these things we want is rather more fragile in the brain. It's rather more constrained anatomically to tinier systems, to more functionally fragile systems, to neurochemically limited systems, smaller systems. So pleasure liking is different from wanting, and maybe pleasures are fewer and farther between in our lives than intense wants. For wanting itself, addiction is interesting. The systems didn't evolve for that, but we're all vulnerable to it, and some are much more vulnerable than others. And we'd like to understand how it taps into the natural systems to amplify the intensity of a want, but also to narrow the focus to just one particular thing, while others might not be wanted so much. And then a final point for today is kind of a surprise to me. A lot of this has been a surprise to me along the way, but kind of a special surprise is that emotional experiences and processes as different from each other as wanting and fear, as desire and dread, which are so opposite in valence from each other, may still have something in common in their mechanisms in the brain, and they may share some kind of in common psychological processes that we'd like to understand a bit better too. So that's what we'll talk about today. To kind of start with wanting and liking, one almost surprise that's emerged and bubbled up gradually over 40 years is that all kinds of different rewards tap into the same brain systems. This first emerged in animal studies looking at dopamine systems, for example, with drugs and sex and food and electrode rewards, those sensory rewards. But in the last 10 years or so with neuroimaging, it's become clear that even human abstract and cultural and cognitive rewards tap into these same brain systems. This I wouldn't have expected, actually. I can remember doing a study about 10 years ago in collaboration with Israel Lieberson, a psychiatrist at Michigan, and we were kind of expecting that sensory rewards in humans, like foods, would light up subcortically, and that cognitive social rewards would light up more cortically, just the division. That didn't happen. I think what's happening instead is that the same reward system is being activated by lots of different kinds of things. Sensory rewards, yes, like sex and drugs. Also for humans, favorite music for music students at McGill University who can pick a favorite piece of music that gives them chills. These brain mesolimbic accumbens systems light up, dopamine systems light up when they listen to that. And even something as abstract as general well-being or happiness. This particular study is from Richie Davidson's lab at Wisconsin, looking at sort of a subjective measure of positive well-being in older adults. They're just rating whether they feel happy and confident about themselves and their lives. And here we're seeing activation in the nucleus accumbens, mesolimbic sensory reward system, but it's sort of correlated, it's lighting up with this general sense of sustained well-being. Very, very abstract. So what's this kind of saying is that there's a surprising degree of sharing by different kinds of positive rewards of these same basic brain systems. Psychologically, of course, reward is more complex. This is a figure from Terry Robinson that tried to divide up wanting, learning, and liking processes in various ways, cognitive versions and more basic sort of Pavlovian triggered versions, conscious versions, and versions that could happen without consciousness. But rather than get lost in the detail, we can kind of simplify it, as Alex pointed out, by just sort of saying categorically there's going to be components of reward. Rewards are things We commonly like. There is such a thing as pleasure. We'd like to understand how liking happens and is generated by the brain. There's wanting. We want those things. We have most of the things we want and like we've learned about in our lives. So these are the components we want to understand and reward. And let's think about wanting first, which kind of famously evolved out of studies from dopamine and mesolimbic systems, but now is involving lots of other brain systems too. The original focus on dopamine really started with Roy Wise in the late 1970s, early 80s, when he advocated the famous hypothesis that dopamine was the pleasure transmitter, still in many textbooks today, and we see it in the media all the time. Dopamine was liking mechanism for reward. And I believed this in the 1980s. I used to teach it in my biopsychology of motivation classes. I loved his evidence. And we once teamed up in the 80s to kind of test this hypothesis that dopamine was where yumminess happened, the dopamine synapses. And the results didn't turn out that way. To my surprise, we couldn't find evidence that dopamine was liking in our hands, and that began us looking at the notion that dopamine was wanting, and lots of evidence in the 1990s and 2000s were sort of going in that direction. But rather than look at old evidence, let's look at something kind of more recent and new that kind of illustrates it concretely, extending a little bit beyond the dopamine system. We've been focused on dopamine for a long time, this mesolimbic system, but it's interacting with a lot of other structures. And one interesting, particularly interesting structure for me, particularly interesting from the point of view of understanding what happens to make us want this but not that in normal life when this and that change from moment to moment, but also in addiction where we get focused especially on one thing kind of persistently, what makes us want narrowly one particular thing. There's interesting interactions of the amygdala with this mesolimbic system. And let me give you one concrete example of this. This is a recent study done by Mike Robinson and Shelley Warlow in our lab using optogenetics to stimulate the central amygdala. And what we're going to try to create is a very intense want that gets very narrowly focused on a target through learning, but detaches from liking and detaches from other normal qualities of reward. So let's sort of see it here. What we're going to see, to point out the paradigm, is this rat's going to have sort of a happy choice in life. It's going to have be presented with the opportunity to press two levers. It can choose which one it wants to press. Both levers give a nice outcome. This lever, if it presses it, it earns a sugar pellet, which the rat likes and wants. This other lever, if it presses, earns the same sugar pellet, an equal sugar pellet, but it also is going to be accompanied by optogenetic laser stimulation of its central nucleus of the amygdala. Most of you probably know about optogenetics, but just in case you don't, it's going to stimulate the amygdala using light. There's a couple steps to do this. In the first step, a microinjection of a virus is put into the amygdala, the central nucleus. The virus is carrying a gene for an opsin photoreceptor, just like the photoreceptors in the back of our eye. The molecule for this photoreceptor is just a little simpler. An infected neuron with this gene will make the protein, will make that photoreceptor, and the photoreceptor will migrate to the membrane of the neuron. If you were to shine light on these photoreceptors, once after a few weeks they've migrated to the neuron, it's going to open ion gates in the neurons that create ordinary action potentials, these sodium and calcium gates, so the neuron will fire. That's what will happen here. And it's going to be paired, we're going to see in the situation, with the rat pressing this lever and then earning the sugar pellet. Let's see it. What we're going to see it is first one at a time. First this lever, then that lever, but then the rat will have a choice, and you'll see what it does with the choice. Let's see when we do that. Whoops. Let's see. Here it is. So first we'll see it one at a time, and the question is, does the rat seem really interested in each of these? Let's see first. Kind of loud. So it's pressed that lever, it earned the sugar pellet down there, it got the sugar pellet, and now it's looking around for something else. Here's the other levers popped out. Well, it seems very interested in this too. It's pressing, it's chewing on the lever, gnawing on the lever. It's typical of an incentive salience target to gnaw on the lever. It got the sugar pellet. It seemed to want both equally interested. But what if it gets a choice? So, okay, goes to the laser lever, earns that laser and sugar pellet, got the sugar pellet, it's gone back to the laser lever, seems kind of focused on the laser lever, sort of ignoring this other lever that's out there. It could earn more sugars if it went back and forth because there's an 8-second timeout period, but it seems stuck on that lever, got the sugar pellet and the laser. It's gone back again. Let's maybe give it one more chance. Seems almost obsessed with that laser lever. Gets the sugar pellet, okay. Let's go. Oh, there it looked at the other lever, but went right back to the laser lever. And so this just goes on for the rest of the session. What's happening is it just goes on and on. So the rat is clearly being sort of focused entirely on that one lever. It's ignoring the other lever. It's very, very focused. It's happening from the central nucleus of the amygdala. Wherever you're seeing a red dot here, we've seen the amygdala, half of the brain, and the amygdala. This is the central nucleus. Wherever it's red, you're seeing this 9-to-1 at least amplification. It doesn't happen in the basolateral amygdala. The central nucleus of the amygdala is sort of striatal in its nature. In macro system views, it has a striatal status, whereas the basolateral nucleus is sort of cortical in its status. This comes from Larry Swanson and people like that. And being striatal may be why you can generate intense motivation with it when you stimulate it, like stimulating other striatal structures like nucleus accumbens and even part of neostriatum. In any case, it's happening there. And the question is, for us as psychologists, why is that happening psychologically? Why does it get so focused on that lever? I mean, one possibility is that maybe the laser that makes it want this particular sugar option is somehow making it like that particular sugar option more. Maybe the laser makes it want that sugar lever more because it makes it like the sugar more. Another option would be maybe it wants the laser itself. So we could ask it in both senses, what does it want? First, does it make the rats want the paired sugar because it's making them like that paired sugar more? That would be a possibility, that that sugar tasted better under the laser. How to ask? Well, perhaps to ask in the same way that human parents for millennia, for eons, have asked their human infants, even in early life, whether they like a particular taste or don't like a particular taste. This comes from Jacob Steiner's work in the 1970s and 80s on human infants, and then was extended to rodents by Harvey Grill and Ralph Norgren in the 1970s too. A sugar taste for a human baby on the first day of life, this from Steiner, is giving sugar relaxed face, let's see it again, is seeing relaxed sort of mouth movements and tongue motions and very relaxed face. Here's the rat from underneath. It's getting a sugar infusion painlessly into its mouth through oral cannula at top. We're seeing it from underneath, doing these tongue protrusions and things. We slow it down so you can see occasional lateral tongue protrusions to the sugar. That's to sugar. Here's bitterness. Maybe a bit different. You get a sense. So there's gape, scrunching of the eyes and nose. The rat can't scrunch its eyes and nose. It doesn't have that musculature, but it can gape, it can flail its forelimbs, it can shake its head and do things of that sort. That's sweetness versus bitter, but it's not just sweetness versus bitter. One could take a sweet taste and get a bitter-like reaction. If one created a learned taste aversion to that sweet taste, the rat would respond to it as though it were bitter. One could take a bitter taste or otherwise nasty taste, bitter like morphine, and make the rats like the morphine by repeated experiences with it, make the rats like intense seawater tastes if you created a sodium appetite. So appetites, learned aversions and preferences switch these things, and brain manipulation switch these things if the brain manipulation is changing this liking for the taste. So going back to the laser, does the laser change that liking reaction to the taste? And the answer is no. Here we're seeing just the positive liking reactions to sugar. The black bar is in the absence of laser, the blue bar is in the presence of laser, these positive liking reactions, and there's really no change. It doesn't matter whether the laser's on or off, the rat likes the sugar equally well. So does it want the laser itself? Is it self-stimulating the laser? in addition to going after the sugar? Is that why it went for that laser paired lever? The answer seems to be no. Here we're asking the rat in two different ways. In one way, the rat can earn laser stimulation just by itself, laser stimulation, by touching one of two objects. A spout, metal spout pops out like this here. If the rat touches it, it gets laser stimulation. This other spout gives nothing, so the rat could self-stimulate just by touching the spout, but it doesn't. Here it's touching equally these two spouts. It doesn't seem to care. It just samples a couple touches at low levels. There's another easier way to ask if a rat would self-stimulate the laser, in case this was too complicated. The way that Jim Olds and Peter Milner originally discovered brain stimulation in rats was to put the rat on a table and then turn the electrode on whenever the rat went to a particular corner, and to see if the rat would stay in that corner. So here's the situation where the rat can earn this stimulation by being put into this chamber. The center is occluded, but it can walk around the corridors, just like the building corridor walking around the outside corridor. And if it goes to this corner, it gets the laser. The size of the circle tells us it's spending about 25% in this corner and equal percent in all corners. It's just wandering randomly. It doesn't care. It doesn't seek out the laser. It doesn't avoid the laser. It just doesn't care about the laser unless the laser is pasted on the sugar. If the laser is pasted on the sensory reward of sugar, this sensory reward becomes incredibly, as you saw, intensely sought after. It's not just sugars. It's not just sugars. This will also work for cocaine, too, as an intravenous, a different kind of sensory reward, intravenous cocaine. This is an experiment by Shelley Warlow. The rat has a choice. It can earn intravenous cocaine equally by two different ways, just like for the sugar. It can make a nose poke into one hole and earn intravenous cocaine, or it can make a nose poke into the other hole and earn intravenous cocaine with the laser. And we're going to see it's going to control its choice just like we did with the sugar. Let's see that. So here's intravenous cocaine. Here the rat has intravenous cocaine coming through this cannula. It's totally painless, and it has the laser tubes here, no pain. So it just earned cocaine, and it's getting the infusion. There's no laser on this porthole. This time this will be the laser porthole. The other porthole comes out, it pokes, it earns the infusion, and it's getting the laser. So there it goes. You can see it seems eager. Now it's going to get a choice. Both portholes will come out. Oh, it looks at this. It looks at this, doesn't poke deep enough to earn, goes back to this, earns its cocaine, and it's going to stay on this porthole now for the entire rest of the session. It'll just stay entirely focused on that, and it'll ignore this again. It goes on until the very end of the session this way. It stays equally focused, and at the very end we start to see a kind of consumatory reaction towards the metal porthole that's very characteristic of incentive salience. You saw with the lever, the rat tried to nibble the levers that were paired with sugar, as though the levers themselves, the metal was sugar. Here we start to see a consumatory reaction to the metal porthole at the end of the session that we've never seen to cocaine before. But the laser makes it. There it goes. It's doing ingestive, biting-like responses to the cocaine CS. Slow it down. Rats normally approach a cocaine CS, but they just sniff it and stay away from it. With the laser, it's making this so intensely interesting an object to the rat that it's generating this entirely new way of reacting to it. It's trying to eat or bite. Here's a different rat getting its laser at the end of the session. It's loaded up on cocaine, she is, at the end of this half-hour session. So we're seeing stereotypies and little sniffing stereotypies. But here we're going to see in a minute. She tried to bite, couldn't really bite as well as the first rat on that one. But let's see. There she goes, and she actually pulled that out a little bit. That was an intense bite. That just doesn't happen to cocaine CSs, except with the amygdala stimulation paired with this laser. It's making it very intense, very able to elicit responses that are unusual. The light power in this is about 10 milliwatts, although it also works at going down to 1 milliwatt, the laser illumination. In this case, it's being pulsed, about 25 pulses per second, but it seems to also work with a constant illumination at low intensities. So we think it's kind of robust. You can change the parameters of the laser stimulation, and you'll still get this kind of thing. It's really quite robust. It's making it attractive. What's interesting to me about this psychologically is partly that it's making this. Many brain manipulations of these green systems that turn on wanting will change the level of wanting and give you intense wanting. But often it goes to lots of different potential targets. The amygdala stimulation is making this one thing wanted while the others get ignored. You can see that. But also there's something else psychologically unique about that amygdala stimulation, and that is that most things that intensify wanting will serve as reinforcers by themselves. Rats will self-stimulate or will work to get microinjections of dopamine in their brain or things like this. The laser by itself is worthless. What we think it's doing is transforming the representation of the sensory reward, the sugar lever or that cocaine porthole. It's amplifying somehow the incentive value of those representations. It can transform, but it's not transferring value. It's not transferring value from the laser to the CS, not a transfer from, as usual, in the usual associative way. It's transforming without having to be by itself a reinforcer. And it's kind of giving us insight into the possibility that motivation can be generated de novo by the brain. It doesn't have to be transferred from this to that. It's generated actively by the brain. It's focused by these systems, and this central amygdala is able to do it. So it's interesting. But most of the reason it's interesting is because it's different. Most of the other manipulations of these green systems, including the original electrode, would have been able to support self-stimulation, right? Most of it was. So Jim Olds, who did the original putting the rat on the table, here we're seeing a photograph from them in 1954, where the rat's there in the chamber and earning the self-stimulation, and Jim Olds turned it on, as Peter Milner recounts in this particular place. Here's the electrode in the rat. You can see the reconstruction is activating the septum. It's activating the nucleus accumbens. It was soon after Jim Olds did this electrode, these kinds of electrodes were implanted in human beings, in people. Sorry, this one is in the rat, in the nucleus accumbens. This is in the human being. Robert Heath implanted it in people down at Tulane University. It's always been famous as a pleasure electrode because it was able to support self-stimulation. And a few years ago, actually 20 years ago, we began to look at some of these electrodes that are clearly able to support self-stimulation and to ask, were they really pleasure electrodes? One hypothesis was that these pleasure electrodes, it turned out that they weren't only self-stimulating, but they were also highly motivating. So if you turned on the electrode in a rat, the rat would eat. If you just turned it on freely, or the rat would drink more, or the rat would engage in sex, or the rat would engage in maternal behavior or other motivated behaviors. It was idiosyncratic for rats. And one hypothesis was that the electrodes were motivating because they were pleasurable. That just as the rat would work to turn on the pleasurable electrode, the electrode would make food more pleasant, would make water more pleasant, would make the motivated target more pleasant. The electrode would do what the laser failed to do. So we asked this 20 years ago with Elliot Wallenstein, who was turning on the electrode and getting the rats to eat. And he had a number of rats who would turn on this mesolimbic systems through an electrode in the lateral hypothalamus that would activate the mesolimbic system, including dopamine system. And they would make the rats eat 4 times as much as when the electrode was off. So we asked if it would make the rats like what it was eating. And the answer was really not so much. The electrode really didn't change the liking reactions to sugar. If anything, what the electrode did was make sugar, which was normally only pleasant and not eliciting aversive reactions, it made the sugar elicit more aversive, disliking reactions, as though the sugar were somehow more bitter under the electrode. It didn't make them want to eat more because it made them like more. Instead, it made them want to eat more, despite making them, if anything, dislike the food more. Well, that was kind of a puzzle, and it fed into the wanting versus liking notion that wanting could be separated from liking. But it left me puzzled because wasn't it a pleasure electrode? And it was still, of course, possible that the electrode itself was pleasant, even if it wasn't making food pleasant. So I looked with Morten Kringelbach, a colleague at Oxford University. We've been looking for the past few years at human self-stimulation electrode literature and looking to see, was it really pleasure? Some of the early studies done soon after Jim Olds' discovery were by Robert Heath here. He implanted patients down at Tulane with these deep brain stimulation electrodes. One of his most famous was B19. He was 20 years old, implanted because he had depression, he was gay, he was drug addict, he had been recently discharged from the Army for a number of reasons. In 1960, he was in this institution. Heath gave him an electrode. And he had a button box that he could press to stimulate it, and this is what would happen. He would press the button box over 1,000 times in a single 3-hour session. At the end of the session, he'd protest, please don't take it away, give me just a few more presses. He was strongly motivated to press. Heath wrote that he had feelings of alertness and warmth during the electrode. He had feelings of sexual arousal and described a compulsion to masturbate. These electrodes are always motivating when freely given. But is it really pleasure? You can read the 1972 paper. You won't find any exclamations of pleasure by B19. Later in his life, Heath wrote a book in the 1990s summing up his career, and there's a page in which Heath wonders, why didn't my patients exclaim with pleasure? I gave them pleasure electrodes. Why didn't they say, and this feels nice, or say, wow, that's great? And he says, well, people have trouble talking about their emotional experiences. Which is undoubtedly true. But still, one could have found exclamations of pleasure, they just weren't there. The electrode certainly never substituted for the pleasure of sex. The electrode only made him motivated more to pursue the pleasure of sex. He was motivated to pursue sex just like he was motivated to press the button more. It's hard to tell from those old cases. There are more recent implantation cases. So here's a case in the last decade in Germany implanting electrodes right in the nucleus accumbens. These were patients who had depression. And these electrodes helped the patients. The clinicians' ratings of whether the patients were depressed improved after the electrode stimulation. These patients, they don't have a button box any longer. The electrodes are computer programmed, so the electrodes just come on and they activate in sort of pre-programmed sessions, but you can control that activation. It would increase activation in the nucleus accumbens and in the amygdala. There were no liking effects. This is a quotation from the paper. There were no liking effects during stimulation in contrast to findings reported by Heath. The patients didn't say these electrodes were pleasant. In fact, the patients more or less couldn't tell the physician whether the electrode was on or off. They couldn't seem to tell. They didn't know whether their electrode was on or off. Yet there were effects if you were talking with them and watching them. Here's an effect. Even motivations were evoked. Immediately after switching the stimulation on, one patient spontaneously reported that he realized he was in Cologne, the city of Cologne in Germany, and that he had never visited the famous Cologne Cathedral. And he planned on doing this, visiting the cathedral in the immediate future, which indeed he did the day following the operation, the release from the clinic. A second patient, when the electrode was on, spontaneously mentioned that she wished to take up bowling again, a pastime that she had done 12 years ago, but hadn't really done since. The prospects of these potential things to do become more inviting. Whether bowling or visiting the cathedral actually becomes more pleasant under the electrode, we don't know. But what it's doing is activating, making things more attractive as prospects without activating pleasure in its moment. All of this is just to say that it is possible to turn on manifestations of wanting to do something or wanting to consume something without having to turn on the liking for it at that moment. It seems possible from the animals with these taste reactivity kinds of data. It seems possible even in people to turn it on with these electrodes. They're not necessarily pleasant. I would love to know whether there are pleasure electrodes. There ought to be. But I think if you look at the literature, it's very hard to find clear cases so far of a unambiguously true pleasure electrode. It's something that would be great to pursue because these deep brain stimulations are being done now again today. The notion that wanting could be turned on without liking was combined with my colleague Terry Robinson 20 years ago into this incentive sensitization theory of addiction, the notion that addicts could have wants that could grow and grow over time even if likes for their drugs didn't grow, even if the likes for the drugs declined. To get this incentive sensitization theory, we needed first the notion that wanting could happen without liking through mesolimbic systems, but also something that Terry Robinson and colleagues like him had shown through the 1980s, and which still is true, which is that drugs of abuse, they don't only activate dopamine systems, they famously activate dopamine systems, but they can also sensitize those systems. And to sensitize the systems means to make it hyper-reactive. Sensitization doesn't make the system constantly hyperactive. It's not constantly spurting more dopamine, but it's hyper-reactive so that it looks normal until you take the drug again, and then it elicits more dopamine. It looks normal until you encounter cues associated with the drug, and then it elicits more dopamine. Sensitization happens because of changes in the dopamine neuron, changes in the tegmental neurons, changes in synapses onto the dopamine neurons, changes in the nucleus accumbens neurons that dopamine talks to, changes throughout the entire circuit. The sensitization changes happen. They're caused by many different drugs of abuse. Opioids, amphetamines, cocaine, alcohol can do it. Tobacco, nicotine can do it. It can happen at the same time. Sensitization can happen at the same time that a drug is inducing tolerance in mesolimbic systems, even though sensitization and tolerance are basically opposite. Tolerance means to be less responsive, to be hyporeactive. Tolerance happens because as you're bombarding with the drug again and again, the neurons start to take back some of their receptors, for example, to digest, downregulate dopamine receptors, D2 receptors, for example. So tolerance goes down. Tolerance reduces those receptors. But if you stop taking the drug for long enough, a lot of the tolerance changes reverse. Sensitization can happen in parallel with tolerance because they're happening in parallel molecular mechanisms within the neuron, parallel molecular cascades. Tolerance tends to dominate early on as long as you keep taking the drug. But when you stop taking the drug, tolerance goes away more or less, and sensitization does not go away. When you stop taking a drug, sensitization can even what's called incubate and become stronger over the month or so that you've stopped taking the drug. If you're susceptible to sensitization, then it expresses, and once it's expressed, it can last years. It lasts years in rats. A rat only lives 2 years, so that's nearly a lifetime. It lasts at least a year in human studies that have been done to track it out. Does it last half a lifetime? No one knows. That hasn't been looked at yet, but that's a possibility. If it's induced, it lasts. But we're not all equally susceptible to having sensitization induced in us by drugs. Some rats can be given these drugs and not get sensitized, while others are getting the same doses and get heavily sensitized. Some people should be expected to get sensitized while others don't too. Anyone can be sensitized if you take enough of these drugs, but at street-like doses, some sensitize and some don't. What determines the sensitization vulnerability are genes, certainly genes. There's sex differences, there's effects of sex hormones. Prior stress can facilitate later drug sensitization. Other states can do this, prior traumatic stress. So there's various things that determine whether we're vulnerable or not. But once it happens, if it happens, then a sensitized dopamine system could produce this sort of signature. That was the notion of the theory. The theory, I thought it would last for a few years and then kind of be replaced. It hasn't, so I feel almost embarrassed that I'm still talking about the same theory 20 years ago. The problem with addiction, though, is that there's too many theories. There's lots of theories. Do you take it, are addicts because they're in withdrawal? Are addicts because they can't feel pleasure? Because they're in stress? Because they have overlearned habits? Because they have over expectations of predictions about the goodness of rewards? All of these hypotheses are in the literature, and they just remain there because that's the nature of addiction. It's a very messy field, and these hypotheses, they just won't go away. But it'd be nice to have a cleaner case, and I think, although it's very sad, there's a new phenomenon in the last 10 years that's really popping up that is kind of a clean case. And this happens in certain Parkinson's patients who are being given certain medications, new medications. The old medications for Parkinson's disease, that was L-DOPA, which made the remaining neurons just make some dopamine and release it. The new medications for Parkinson's disease are direct agonist medications that they don't stimulate natural dopamine release. They plug right into dopamine receptors and turn on the postsynaptic dopamine receptors. These are D2, D3 agonists. One interesting thing that pops up in about 15 to 20% of patients who are getting these new medications is a phenomenon called dopamine dysregulation syndrome. One feature of this is that people can start becoming addicted to their medication almost as though they were addicted to a drug of abuse. So some patients start to demand far too much L-DOPA, far more than their physician wants to prescribe them. They overconsume the L-DOPA. You can actually look then at whether they like those L-DOPA. People don't usually like L-DOPA very much. It's not like cocaine or amphetamine. But you can ask these patients, how about them? Do they want or like these drugs? And you can actually measure dopamine release in their brains while they're getting the drug. So this study was by Evans et al. They're measuring, it's a PET study, measuring dopamine release through labeled raclopride binding. And what they're doing is plotting dopamine release, which is on the vertical axis here, against the patient's own subjective ratings of how much they want to take more drug. Do you want to take more L-Dopa? The more dopamine you have released, the more you want to take more L-Dopa. It isn't just triggered when you're not taking the drug. It's not just triggered by withdrawal feelings, although withdrawal feelings still can happen to these patients when they don't take the drug. They take the drug, and the desire doesn't go away. It gets stronger and stronger. The dopamine release doesn't really correlate with their liking of this drug. So it's kind of turning on the wanting of the drug without turning on the liking of the drug. It's kind of a pure case, and it's free of a lot of the social explanations for addictions. These are not people who are taking it because their peers pressure them to take it. They're not taking it to escape nasty cases of life stress. These patients also show behavioral addictions while they're taking the medication. Things like compulsive gambling to the point where they're losing their family savings, or compulsive sex and pornography, especially internet pornography, use and seeking, but also sometimes sexual behaviors that sometimes become problematic in the sense that they can be illegal. Compulsive shopping, compulsive binge eating sometimes, compulsive punding, which is things like sorting through drawers, organizing buttons in drawers and things like that. Compulsive hobbies. It happens in about 15% of the patients taking the agonist medication. Why is it happening? Well, here's a paper just a couple of years ago by O'Sullivan et al. With the Evans group, suggesting that the patients who are showing this have higher dopamine release. What we're seeing here is L-Dopa elicited dopamine release in the striatum, the caudate putamen, and in the nucleus accumbens, the ventral striatum, elicited by taking a dose of L-Dopa. And what you can see is that the blue bars, the patients who have these compulsive disorders, have higher dopamine release stimulated by taking the drugs than ordinary Parkinson's patients who have equal Parkinson's disease but who don't show this compulsive kinds of motivation. And there's limbic activations triggered by this too. So basically it's kind of saying, if one could have created a person who's not socially prone to be an addict, not experiencing the usual life experiences that lead one, and just make them an addict by stimulating their dopamine system, what would it look like? Well, it seems to be looking like this. One could ask whether they're finding great pleasure in all of these things, and those studies should be done. I don't think it's been done enough yet. My prediction is going to be most of these patients are not getting tremendous enjoyment from a lot of this that they're doing. That's certainly not coming through in the report so far. In any case, wanting, whether it's triggered by addictions, they're triggered typically by cues. To get the best sensitized dopamine release in a neuroimaging scanner, you would show patients, you show addicts things like these visual cues that elicit associated with the drugs. You'd show binge eaters and say obese binge eaters who also have hypersensitive reactions in mesolimbic systems to the sight of foods. You show them things like this. The behavioral addictions, work is just coming out in the last few years on neuroimaging. Visual cues like this will turn it on, and a hyper-reactive limbic response. But all of it's tapping into just ordinary systems that exist in all of us. Any of us could be plopped into the scanners, and things that people are motivated by, especially advertising kinds of things that could trigger urges in us, would trigger these in us. So it's not so much a qualitatively new phenomenon that creates these addictions. It's really just an amplification and a focusing on these kinds of cues, similar to what that amygdala system may have done. So all of that's wanting. It kind of leaves us with a vacuum to explain liking. I used to be asked at so many talks, if dopamine and all of this is wanting, then what's causing liking? Pleasure exists. It exists in our lives. It has to have a brain cause, and even we can find some brain causes in the form of these little hedonic red hotspots that are activating here. Let me give you a quick example of a brain hedonic hotspot and how it does the liking. They're smaller. They're usually tucked within these larger structures. They're neurochemically restricted. So here's one. Let's take it. They're interactive. Turning on one tends to turn on another hotspot. They need to be interactive. If you turn on one hotspot and suppress another, you don't get intense pleasure. You need to let them all come on together. There's several of them. One is, or two are in the prefrontal cortex. There's one in the nucleus accumbens. There's one in the ventral pallidum. There may be even one in the brainstem. They're all sort of functionally interconnected. As an example, let's look at the nucleus accumbens one. Focus in on that. Here's the nucleus accumbens in the sagittal brain. Let's blow it up here. What we're seeing here is a blow up of just this section here. These colors, it looks a little bit like a neuroimaging map, but it's not a neuroimaging map. You're not seeing neural activity here. This is a causation map. It's a psychological causation map of neural events causing something psychologically. And what we're seeing here, every little splotch here is a microinjection of a drug. It's an opioid stimulating drug, Damgo, that stimulates mu-opioid receptors, every little splotch. We know the size of the splotch because we can measure how wide a splotch neurons are activated by looking at phos plumes that are activated. That's the size of the splotch. But the color of the splotch is what it's doing in its behavioral consequences and psychological consequences. Wherever it's green, it's turning on wanting to eat in these rats. These splotches are doing. It's making the rats eat twice as much of normal, or 4 times as much as normal, or 8 times as much as normal. It's really making them eat a lot. They want to eat a lot when they get these stimulations. The green extends under the red and orange just like a carpet. It extends throughout the entire nucleus accumbens. This is the entire nucleus accumbens. It would extend out from the wall. This is the medial shell of the nucleus accumbens. It would fill up the lateral shell and the core. It would extend upwards into other parts, lots of those green brain structures that you saw on the other figures. It extends widely. But wherever it's orange, it's doing something else in addition. It's not just stimulating wanting, but it's also increasing the liking for what's wanted. It's increasing the liking reactions to sugar by doubling them or tripling them in some cases. And all the splotches that enhance liking are clustered. They didn't have to be clustered. We didn't expect them to be clustered in the beginning. They're clustered to about 1/3 of the nucleus accumbens shell in this slide. That's about 1/10 of the entire nucleus accumbens if you put in the core as well. 1/10 of the nucleus accumbens really is this red little hot spot. The rest of the nucleus accumbens, 90% of it is just green. We do the same microinjections, we don't get. You get the green throughout. Some microinjections will suppress nastiness as well as making you want to eat more, but just this hotspot version will do the triple whammy of making things more liked, making nasty things less disliked, and turning on the wanting too. This study was like 10 years old from Susanna Pathenia, but recently Daniel Castro replicated that. Here's his mu hotspot. This is again the nucleus accumbens just blown up here. He replicated it with the red hotspot here for mu microinjections, and he kind of substantiated what was hinted at in Susanna's earlier data, that there's a cold spot in the caudal shell. This is rostral shell anterior, this is posterior shell. There's a cold spot where the liking reactions get suppressed by the opioid, even though its wanting to eat is still as intensely amplified as in the hot spot. But he also extended it to other kinds of opioid stimulations like delta and kappa. And to our great surprise, the hot spot and cold spot organization extended to both delta as well as to kappa. For delta, it's kind of okay because delta and mu are reward-like opioid signals in the literature. But kappa is usually associated with nasty events. Kappa is released in rats will work to avoid it. They'll avoid a place that stimulates kappa. It's associated with pain and drug withdrawal and things like that in humans. There's only one site in the brain, as far as we know so far, where kappa is actually turning on something positive like liking reactions, and that's the hedonic hotspot of the nucleus accumbens shell. We couldn't quite believe it, so we said, well, let's not trust liking reactions to sugar. Let's try a different way. And Daniel asked, by conditioned place preference, would the opioid microinjections induce a conditioned place preference? And they did, even for kappa, but only in the hot spot of that nucleus accumbens. Wherever the kappa was done elsewhere, the rats would avoid the place. There's something unique about the hot spot. It turns out, although no one knew it before the hot spot was found, it turns out that the nucleus accumbens is not homogeneous. There are different anatomical projections from the hot spot to targets. It's getting different inputs from the rest of the nucleus accumbens. Larry Swanson's group has shown that. There's neurochemical differences too. It's neurobiologically different. There are subcompartments in this nucleus accumbens shell. That's the nucleus accumbens. I used to think that hedonic hotspots would exist only in subcortical structures like the nucleus accumbens and ventral pallidum and such. I used to think that the cortex wouldn't have hotspots because it turns out people who have had prefrontal cortex damage, they don't actually lose the capacity for pleasure. People have distorted judgments. They make bad decisions in life after they've had prefrontal cortex damage. But you give them nice things and they exclaim with pleasure. They will work for these nice things. They seem to enjoy them. There's no evidence that pleasure is lost. So this cortex doesn't really seem to be necessary for normal hedonic reactions. But it may be sufficient for intensifying them. Daniel Castro has recently been looking at the cortex. Here we're seeing a lateral surface of the rat brain's cortex, the lateral orbital frontal, the insula cortex. These are taste areas and then aftertaste areas. Here we're seeing the medial surface of the cortex, the medial orbital frontal and the anterior cingulate cortex, rat regions of anterior cingulate cortex. He's doing microinjections through here, and what he's found is there are hotspots. This basically is one hotspot in the orbital frontal cortex, the sort of medial bit of the lateral surface and extending right into the medial surface of the brain, what will become anterior cingulate cortex. It's turning on these liking reactions, tripling them very, very powerfully. There's another hedonic hotspot in the insula, posterior insula. There's a sort of cold spot that is bookended by the two hotspots that exist between them. The liking hotspots are again localized. Wanting to eat is elicited much more widely but throughout, including in the anterior cingulate, like by comparison. So the cortex is participating to intensify hedonic reactions, at least through these hotspot things. Even though you can take it away, it doesn't seem so necessary for the normal hedonic reactions. So in any case, we're left with these hedonic amplifying hotspots connected into a circuit. I haven't shown you evidence that they turn each other on, but they do, and that you need to have them unanimously turned on to turn them on. Turn them on together, you can get liking as well. It's a little trickier to turn them on than to turn on wanting. That may be why pleasures are less frequent in our lives than wants and sort, but there is a way of seeing them. The last thing I'll say about hotspots is that they're not all alike. The cortex, I said, you can take it away and you don't lose normal hedonic reactions. Same is true for the nucleus accumbens. There's only one site in the brain where if you take it away, normal pleasures turn to terrible disgusts, where sweetness becomes actually disgusting and gaped to as though it were bitterness. Only one site in the brain, and that's the ventral pallidum hotspot. The ventral pallidum has its own hotspot in the posterior ventral pallidum where you can enhance hedonic reactions. It's the only site in the brain where loss of neurons makes nice things disgusting. Whenever I say that, I can't really believe that I'm hearing myself say it, because how can it be that there's one site in the brain where, when lost, would do this? It has to say something important about the brain. Why is it just the posterior ventral pallidum? I don't know why it's just the posterior ventral pallidum, but it makes it a very interesting structure from the point of view of understanding affect, worthy of paying attention to and looking at in future. The very last point for today is this notion, which was also a big surprise to me at least, that mechanisms for wanting overlap strangely with mechanisms for a kind of fear, for a kind of dread. We've seen modules in the nucleus accumbens already in the form of a hot spot versus cold spot, sort of sub-modules or subregions in the nucleus accumbens. Let's look at the nucleus accumbens one last time and tweak it in just a slightly different way to see these modules again. We're going to see them behave. This is relevant even if you're not interested in these nucleus accumbens modules. It might be relevant if you're interested in emotion in general, because there's a problem that bothers me, and it may bother anyone who teaches emotion and affective neuroscience, and that is that the brain structures that turn on for one particular emotion tend to be the same brain structures that turn on for a different emotion. As I say, sometimes if you're teaching affective neuroscience and you give an exam question to the class, did you read the article by Damasio or by you name your favorite affective neuroscience, on happiness, on joy, on disgust, on anger, on fear? Did you read that article? Do you remember which structures lit up in the brain? List 3 of the brain structures that lit up to happiness or fear or anger or joy or pleasure. You don't have to read the article. If you can remember any of these structures, list 3 of these, you'll probably at least get a B on the exam, and you may get an A. because it's the usual culprits again and again and again. This slide from Lisa Feldman-Barrett and Torweger is simply showing that for one particular structure, the insula, which had a hedonic hotspot, it's been implicated in neuroimaging studies of happiness and pleasure, great, hedonic hotspot, but also for fear, anger, for guilt, for sadness, for disgust. All the emotions seem to light it up. Anybody who wants to understand how happiness is generated differently from fear has to be frustrated by this. Why is it that this usual culprits? What's going on? So maybe a potential answer comes from this nucleus accumbens things. A slightly different way of tweaking the nucleus accumbens from the opioid microinjections that I showed you is to tweak it with a microinjection of something that sort of makes the neurons inhibited. There's a notion that the nucleus accumbens turns on reward motivation by inhibiting itself because the nucleus accumbens is made up of GABAergic neurons. GABAergic neurons are always inhibiting other neurons. If you inhibit the nucleus accumbens neurons, you release the targets from inhibition. The targets are disinhibited, they're excited, they can generate the motivations. Indeed, you can generate intense motivations, rewards, and things. Many drugs of abuse will hyperpolarize the neurons. Let's hyperpolarize them with a microinjection that cuts off all incoming glutamate excitation signals from the cortex. This is DNQX doing it. Wherever it's green, you're seeing intense positive reward-like motivations that makes the rats eat more, where it's green. It makes them learn a conditioned place preference, so they prefer a place where green microinjections are happening. Some hyperpolarizing microinjections can make them like the sugars that they're eating more. So all of this is happening in these anterior sites where it's green. Wherever it's red, it's really not making them eat more. It's green, big eating here. Wherever it's red, it's triggering different behaviors, sort of fearful behaviors. Our rats are very tame. We're a reward lab. We like to make pets of our rats, in a sense. Before any experiments, the rat come in, it walks around on a student wearing a lab coat, the student has M&Ms in the pocket, the student can feed the rat M&Ms, the rat can find M&Ms, this happens. It's like we want the rats to be comfortable because we want to study wanting and liking. Our rats don't try to bite us. They're sort of pet rats. But wherever you see a red microinjection, it's the same drug, the DNQX, in the back of the nucleus accumbens. Wherever it's red, the rats do try to bite us. If you try to touch them after this red microinjection, they will try to bite you. If they can avoid you, they will. They'll try to get away. They'll squeak when you try to touch them. They'll jump over the wall if they can. If you do grab them, they'll bite you. And if you just leave them alone, they'll show anti-predator sort of defensive burying, which ground squirrels in California will do to rattlesnakes who approach their burrow. Mice will do to scorpions, defensively bury the thing with bedding and sand that's around. Rats will do it to a poison-paired food or to an electrified shock prod that's sticking out into their cage. If they touch this, they get an electric shock, so they don't touch it, but they bury it. And these rats, after a red microinjection, will defensively bury towards us. They'll defensively tread and bury towards us. If you're out there, if I'm the rat, and you're out there looking at me, they'll defensively bury, and there'll be sort of a wall of burying that ends up here. After the red microinjection, fear of some sort. And wherever it's yellow, it's doing both, eliciting eating and eliciting these fearful behaviors. Wherever it's yellow, it's doing both in the same rat in the same hour. It's like a little keyboard of desire to dread. The desire is sort of going down, the dread behaviors are going up as you go caudally, and it's yellow in the mixture. It's valently tuned, but it's not inflexibly valently tuned. You can retune that keyboard. You can retune it. And the very last thing I'll show you is the same experiment I just showed you, but done by several people in our lab, Sheila Reynolds and Jocelyn Richards, doing the same microinjections just in 3 different environmental situations. In one case, the microinjections are done in the rat's own home room. It's dark, it's quiet, it smells like rats. Or it's done in the regular lab, a room like this. Or it's done in a regular lab, but we turn up the lights and we play them. Yes, so I don't like that after a while. That music jars on me. Iggy Pop was a former student at the University of Michigan. He never graduated. He was doing something else on the side, and he dropped out at some point. My graduate student likes his music, and so we used it to play to the rats. The rats share my taste in music. They don't like Iggy Pop. If you ask them if they would like to turn him on, they can come here. If they'd like to turn him off, they can go there. In the first 15 minutes, they've learned to turn him off. This is Iggy. This is turning him off. By the end of the hour, he's off, 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 and they prefer the standard lab condition to Iggy. But they'd rather be at home than in the lab, so they prefer home over lab. They prefer lab over Iggy. But what if they can't turn him on or off? What if they just get the microinjection and they go into Iggy, or they go into the lab, or they go into home? What happens is, in the lab, you see the three-colored tripartite keyboard just like before. The front is green. There's mixtures of both in the middle. The posterior is all fear, pure fear. If they get it under Iggy, what happens is the fearful zone sort of expands. The mixed zone definitely expands, and the pure reward, appetitive motivation, incentive zone is sort of crammed into the anterior rim. If they get it at home, the reward zone expands. There's still a little bit of sort of pure fear here, but the mixed sites have just about dropped out, and most of the nucleus accumbens is pure reward under these conditions. Now, some sites are switching from green to yellow, or from red to yellow, or yellow to red. But a few sites, as you can see, these are the same rats, are switching from red to green as you can go back and forth from the environment. You can convert. This is a little neural sledgehammer in the brain, this microinjection, doing the same thing each time, but this sledgehammer is eliciting opposite motivational effects depending on whether they're in Iggy or at home. It's a Schachter and Singer kind of experiment. It's an Elliott-Wallenstein kind of experiment. We can change the output of these neural systems, the motivational, psychological output, by doing this. There's something in common between desire and dread. Certainly something in common neurobiologically, possibly something in common psychologically. There's a slight difference between the desire and dread modes of this that's being reprogrammed by the psychological environment. Dopamine, endogenous dopamine, is needed to generate the green desire. It's also needed to generate the red dread. If we block endogenous dopamine by mixing dopamine antagonists into the same DNQX microinjection, we can block the motivations, but slightly differently. To generate desire, even if we took a site in the middle that generated desire only at home, it only needs D1 dopamine inputs. If we block the D1 inputs, no desire. If we block the D2 in dopamine inputs, the desire persists. And here we're seeing desire persisting after the D2 blockade. But if we were to generate fear, even in the same rat, even at the same site, by switching it to Iggy Pop, the dopamine mode right at the microinjection site flips. It still needs D1, but now it also needs D2. D1 and D2, there are different receptors, but they're also activating different pathways out of the nucleus accumbens, which we don't have to dwell on, but there's sort of different circuits. Somehow, the environment is switching the local dopamine mode and potentially the local neurons participating in this microinjection-induced thing. What does it mean psychologically if there's something shared in something like the nucleus accumbens that can generate either desire or fear? Well, people who take amphetamine are euphoric, but sometimes they can flip into psychosis. People who endogenously have psychosis involving feelings like paranoia and fear and suspicion are perceiving objects in the world that many of us might find kind of comforting. If many of us walk on the street and we see a police car, fine, we feel a little safer. Someone who's in a state of paranoia walks out on the street and sees a police car. There's a police car again. Why is this police car here? We can work it into a thought. Why are we being followed? The police are monitoring us again. There is a notion by Satish Kapoor, a psychiatrist now at University College London, who suggests that antipsychotic drugs, which are mostly dopamine blockers, D2 dopamine receptor blockers, work by peeling away a kind of fearful incentive salience, a fearful salience. A person who has desire can't not look at the object of desire. It's attention grabbing. You get drawn in. It triggers an urge for the thing. Rats may nibble on that cue. People who have fearful salience can't not look at that police car or that object of fearful salience, but it's sort of a threatening kind of thing. Kapoor suggests antipsychotics take away the threateningness, take away the compellingness to look at that object that seems to threaten. and that's what provides relief if they take that long enough. So it's conceivable that there's this subcortical dopamine switch that's participating in both desire and dread. I should stop. Just to sum up what I've said, it is possible to split the reward psychologically into liking, wanting, and learning. I haven't talked today so much about learning, but liking and wanting. We can map them to some degree on different brain systems. Pleasure liking is generated by these mostly deep in the brain, the fragile hotspots. Pleasure wanting is robust. It's robust in all of us. We all have lots of wants. They're easily triggered. In some people, especially in addiction, wants can become intensified and narrowly focused. And something that I really don't understand but would love to understand better is how these wanting mechanisms can overlap with fear. What's the nature of the flip? What's the nature psychologically of the overlap? We don't have strong answers to that, but I think that's interesting to think about in the future. So thanks a lot for your patience. I'll stop. And I should say I haven't done any of it. It's really all of these people who have done the experiments and you've heard about. If there are any questions, I'd be happy to take questions. Yeah.
Part of the issue that I might be having is the fact that our language is not built maybe to understand some of these mechanisms. But I take liking, and correct me if I'm wrong about how you're using it, as something that happens during the experience and wanting to be something that happens in anticipation and could be happening during the experience. But is that how you mean the term?
Well, I agree that wanting is usually an anticipatory thing and liking is sort of dominating in the experience. But I think both of them can leak into the other time zones. So as we saw, the patients who were taking L-Dopa wanted to take more most when they were taking some. The actual consumption would make them want more. And lots of us have the experience, the French have the expression, the appetite comes in the eating, right? That you take a morsel and you want more. Conversely, liking is usually in the experience, but we can elicit conditioned liking. We can elicit liking reactions as a conditioned response to a CS paired with liked things. And pleasure can be elicited in lots of people by conditioned things. I said last night or yesterday to the grad seminar, there's the Winnie the Pooh phenomenon. It comes from a Winnie the Pooh book where he says, my favorite thing is my honey pot. But even better than eating in my honey pot is the moment just before I begin eating in my honey pot.
But that's not liking honey.
Well, but it's the best moment for Winnie the Pooh. So, and if we could look at his brain at that moment, would we see an activation in the hedonic hotspots? When I showed you the imaging before of all these things like music, favorite music, eliciting thrills and things, it's eliciting in these nucleus accumbens things. I think liking pleasure, it usually is the experience itself, that's true, but it can be elicited. It's not as strong. I mean, when we do the liking reactions and do that, a CS can elicit about 1/10 the intensity of liking that the UCS actual sugar can. But we can elicit conditioned liking.
The way I think everybody wants money, but it is weird to like money.
Yeah, no, that's true, but money is a little bit special.
Yeah, it's very special.
Yeah. But some people like money.
So will this PPT be sent to us or do we?
Sorry.
So could you just send the PPT to me or to us? Yeah.
Yes, anybody who would like the PowerPoint is welcome to it, and just email me and I can send it. Is that what you want? Ask.
Okay, so this is my first, and the final question is how did you measure quantitatively? Okay, subjective pleasure, incentive value. How did you measure them? Yeah.
How did we measure subjective pleasures and incentive value?
Incentive value, yes.
Right. So that's an excellent question which I have not addressed. Pleasure is subjective, wanting is subjective. Perception is subjective, memory is subjective. All psychological functions are subjective, yet many psychological functions can also be objective even if they're not subjective. So perception can happen in the absence of subjective perception, like implicit, visual, subliminal kinds of things. Implicit memories can happen subliminally or implicitly without being subjective to the experience. Can pleasure and motivation also happen as objective events independently of subjective experience? I believe that they can. I haven't presented any evidence to that, although Shimon and I were talking earlier today about some evidence that Piotr Winkelmann, Bob Zients, and others have provided on that. So what I would claim is I have never, ever measured subjective pleasure or subjective wanting in our rats. I've never measured it in you or you or you. You've never measured it in me. You may have access to your own, but we can all measure objective pleasure reactions in the brain and sometimes in behavior and through each other's and social and verbal kinds of experiences. We get indicators of these subjective things. It is true that in the subjective rating studies, we probably are getting subjective ratings, right? They're saying, I feel pleasure for the Parkinson's patients and stuff. And those are absolutely as good and absolutely as flawed as subjective ratings of anything. They're usually good. We take them at face value. But there may be a difference between subjective ratings and both subjective experience and objective hedonic reactions. What we are measuring are objective hedonic reactions, and we're looking for the neural mechanisms of those.
It seems like the only way to get is just to let the subject, yes, to let the subject write down their subjective rating, yes.
Yes.
It's the only way, yes.
Yes, I agree. One can do that. And one can ask the pleasure electrode person, are they feeling a pleasure? And get them to write it down. Possibly you'll get a clear answer, possibly not so clear.
That was a really beautiful talk, thank you. In your rat central amygdala experiments, did you ever try taking away the cocaine or sugar after the rat had learned to press? And did they keep up their behavior or did it extinguish?
It does extinguish. It does seem sort of, what I think it's the amygdala laser is doing is it is transforming the representation of this sensory reward. It has to be a sensory reward to start with, but then it gets tremendously amplified. Now, if we take away the sensory reward, the representation tracks that, taking it away. And it will know that it's changed and there'll be nothing left. I mean, it'll extinguish down. So that will happen. Yeah.
And do you think there's any particular projection from central amygdala that's responsible for driving this?
I am sure there is some particular projections from central amygdala that's responsible for it, and we're just starting to kind of do that kind of thing. Yeah.
I was just curious, is there a difference between the pleasure of liking something and, say, the pleasure of quenching or satisfying a want?
I think that's an excellent question, and it kind of gets into like 50 years of physiological psychology and the psychology of motivation. It used to be that we thought through Hull and others that all real motivation was focused on satisfying these wants, getting these nasty hunger drives, these nasty thirst drives, even could potentially a disturbing sex drive, stimulating getting these things down. That motivation was drive, and that reward was the reduction of nasty drives. Then around 1960s, 1970s, 1980s, a series of people, Pfaffman, Bowles, Bindra, Totes, kind of showed that even hunger isn't really working as a nasty drive. Like you couldn't condition rats to places to avoid places. You couldn't use hunger reduction so much as a reward. What was rewarding was food. And what hunger would do is amplify the value of food. So motivation kind of switches to an incentive mechanism. So in the end, the hunger of reducing the drive is feeding into the reward of the food. They're not so much separate things as our textbooks might have suggested, I think.
I was interested in, as usual, some of the evolutionary evidence, and you made me think differently, perhaps, about some specific things like being afraid of dark or light, or preferring bitter naturally, or something like that. And I always imagined that had something to do with something peripheral, but it seems to me, given your account, you could make those sort of whole organism changes at the level of those.
Yes, I think those kinds of things are all central and not so much peripheral. I mean, lots of us do like bitter tastes if we drink a beer, for example, or eat cranberry sauce.
I was trying to think the most unalienable thing. I mean, I guess you can get a rodent to like being in the light, but it's difficult.
Yeah, it would be that sort of thing. I mean, yeah, certainly stimuli are a lot of stimuli in the world are intrinsically sort of biased in their valence. Sweetness is kind of nice to all infants. and most kids. Bitterness is nasty. So we start from that. But the niceness is not in the sweetness. The sweetness can be made nasty. Pair a new sweetness with visceral nausea a few times, and it'll be disgusting. Taste aversion learning. Take bitterness and pair it with beer and other things. Take the taste of a cigarette and pair it often enough with things, and these terrible, terrible sensations become savored and liked, at least for some. So it's the brain's reaction to these things. It's not the things themselves that are valence, pleasure and displeasure, I think.
Regarding to central amygdala experiment, does it amplify not wanting as well?
Yes, so absolutely. I mean, the central amygdala, of course, is famous for fear. And how could I even talk about central amygdala in reward motivation? It's very much involved in fear and other aversive kinds of emotions. But just like the nucleus accumbens is famous for reward, yet can generate fear, as you saw, the amygdala can generate both also. It's a puzzle. How is this possible? Is the amygdala changing modes like the nucleus accumbens did? Does the amygdala have separate, segregated, labeled lines within it? Some people think so. But, I mean, this has to be explained. So that's an excellent point. I think you're
Okay, so I'm just kind of curious. I'm thinking about the variation that you see in the propensity to sort of become addict or not to become addict, and I'm wondering if there's anything that relates to individual variation in hotspot size or even sort of the other sort of volume of some of these other wanting areas. I mean, is there anything? To what extent is there individual variation, and
Yes.
might it relate to some of it?
There's massive individual variation, and we want to know what it relates to, right? And so Terry Robinson, for example, has been looking at individual differences in rats having to do with what he calls sign tracking versus goal tracking. You saw that the rats were nibbling on the sugar levers, right? That's sign tracking, nibbling on a metal predictor, a sign that predicts a reward. Other rats, and they'll do that in natural auto-shaping situations too without the laser. They'll do that to a Pavlovian CS. But other individual rats who get the Pavlovian CS lever pop out won't nibble on the lever. They'll run over to the sugar dish and they'll nibble on the dish when the lever comes out. They're called goal trackers. The notion is that sign trackers attribute incentive salience, this dopamine wanting, to the predictor, and they have stronger cue-triggered wants. They self-administer cocaine more when you give them the chance than goal trackers. They show faster acquisition of sensitization. You can sensitize both, but they're more prone to do it. And they have brain differences having to do with dopamine D1 versus D2 RNA in the nucleus accumbens and striatum and things. So there are these differences. The question will be, is sign tracking really the essence of an addictive personality? But to the degree that it is, there are these differences. And to the degree that's not, there will be other individual differences. And
Maybe one more last question.
yes. Oh, sorry.
You mentioned behaviors a bit. I wonder if there's an interesting social role for the like. If you had rat one with the like going on, would other rats be attentive? Would they try to figure out what this rat had gotten into that makes them like so much? Or are they giving off something?
With the liking reaction,
Yeah,
you mean?
is there a-
Not the light, not the laser light, but the liking reaction?
Yeah, the like rather than want.
Yes.
I wonder if there's a very something
Yeah.
that actually signals other rats.
Well, I think it's a great question. Why does liking exist? Why does it? Evolutionarily, psychologically, socially? I don't have a clear answer. I mean, Paul Rozin has written on why does pleasure exist, and his evolution answer is that basically it may open up a reward to new cognitive solutions by having a kind of conscious pleasure. I can imagine an early primitive creature that had only a wanting system and could survive. Seek the things you must eat, and having only a liking system might be harder to survive. I've said this several times to audiences. Usually they say, okay. Sometimes they say, no. I imagine a primitive creature that had only liking. I don't know how evolution worked. I presume they each have functions. Wanting has a simple function to see. The liking one's a little more complicated. Or subtle.
All right, well, why don't we continue, for those that have other questions, to have this conversation over drinks with Statler. Thanks again, Ken.
Sure.
It was a wonderful talk.
Okay. My pleasure.